In this video, we will be discussing solubility, which itself is a form of equilibrium. Solubility is the degree to which solids will dissolve in a solvent based on their solubility constant. This K, or KSP, is the exact same type of K, equilibrium constant, that we've been working with before. The way that our equilibrium constants work in terms of the equilibrium constant equation is products raised to their respective powers divided by reactants raised to their respective powers, leaving out solids and liquids. So when we're talking about the solubility constant, that is the ability for a solid to dissolve in a given solvent. So as a reactant, you will have a solid which breaks apart, if we're talking about aqueous solutions, into ions. The KSP, therefore, would be your products raised to their respective coefficients divided by, well, 1. You would leave out the solid because solids do not change concentration. There are some general rules for predicting trends in solubility. While this table here from the textbook has a large number of different solubility rules, the ones that we will be primarily concerning ourselves with are the ones that don't have many exceptions, and that would be lithium, sodium, potassium, or ammonium. So pretty much anything in the first column and ammonium ions, anything that is bound to them will be soluble. There are no exceptions to this. Similarly, for anions, the nitrate and acetate ion, where that is C2H3O2 minus, anything that is bound to these, so a metal bound to one of these two, will be soluble. There are no exceptions. Chlorides, bromides, and iodides, and in fact all your halides, anything in the next to last column of the periodic table, will be soluble. However, there are a couple of exceptions to this general rule, including silver ions, mercury 2,2+, and the lead 2+ ion. If any of these three metal ions are put in a solution that contains chloride, bromide, or iodide, they will form an insoluble salt. They will, what we call, precipitate out of solution. So if a solid forms when we mix two solutions together, that solid is called a precipitant, and the process of a precipitant forming is called precipitation, kind of like raining, but for a solid. In terms of the other ones, these are ones that are helpful to know, but because we will be using salts to give us some of our ions, particularly if we're talking about Le Chatelier's principle, we would primarily be using either nitrates or something with like a lithium, sodium, potassium, or ammonium, in combination with in the case of this first one, these cations, if we were interested in adding an anion as either a product or a reactant. This is a way of getting one of those ions in solution without adding necessarily a particular reactant. Similarly, if we wanted to add some metal ions, we could add them into the form of the metal nitrate or the metal acetate. And this is how we can play around with the Le Chatelier's principle for reactions that have aqueous components. Now, the way we can determine whether a reaction is going to happen when we mix two solutions together, typically those two solutions will have different salts, is if we are mixing two salts together, we will take the cation from one and the anion from the other and look to see what they form. So let's say we have a solution of potassium iodide, Ki, and if you remember, anything that is bound to a potassium is soluble, so the potassium iodide would be soluble. They would break apart into potassium ions, which are our little white dots, and iodide ions, which are our purple dots. We're reacting this, we will mix this with lead nitrate. All nitrates are soluble, therefore the lead nitrate is soluble. So we get nitrates, NO3-, which are these, and the lead, which will be represented by the yellow dots. If we mix the two together, what we would do is we'd take the metal ion from our first solution and look to see what that forms with the anion, the negative ion of our other solution. So what we would ask ourselves is, does potassium nitrate form a insoluble salt? And the answer is no, it does not. This is soluble, and so it will stay in solution. We then look at the metal ion of our second solution and combine that with the anion from our first. So that would be the lead and the iodide. If we combine lead and iodide, does that form an insoluble salt? The answer is yes. Most iodides are soluble with the exception of lead. So lead iodide should form a solid, and we would therefore see a precipitant. So if we take our potassium iodide, react it with lead nitrate, we would initially have the two mixed together. Our lead ions and our iodide ions would come together to form a solid that would precipitate and drift down to the bottom of our beaker in the form of lead iodide. We would have potassium ions and nitrate ions that would remain in solution. Now, the way that we have previously been writing out our equations would be what we call the molecular equations form, which is we have our, in this case, potassium hydroxide reacting with magnesium nitrate to form potassium nitrate and magnesium hydroxide. So from this, we can see that the magnesium hydroxide is going to be a solid, and everything else will be in aqueous solution. However, what's really going on is that the potassium hydroxide is not bound together. The potassium and the hydroxide will separate once we put them in water. So once they form an aqueous compound, they're going to break apart, and we'll be left with potassium ions and hydroxide ions. So a better way of representing this is in the form of the ionic equation. So the ionic equation takes into account things that when we put them, in this case in water, they break apart. And so when we're writing out our ionic equation, we write it out in the form that they will actually be in solution. So the potassium ions will be separated from the hydroxide ions. So we will not actually have potassium hydroxide. We'll have potassium ions floating around separated from the hydroxide ions. Similarly, our magnesium nitrate is soluble, and so it will actually break apart into magnesium ions and nitrate ions. So we would have magnesium ions and nitrate ions. This would be our reactant condition, right? They are not in the full molecular form. The potassium hydroxide, again, is broken apart into potassium and hydroxide ions. When we mix them together, the potassium and the nitrate don't do anything. They just sit there. We will be calling things that just sit there spectator ions. Spectator ions are those ions that do not participate in the reaction. They are generally just there to bring the two components that are doing the reaction. So in the case of potassium hydroxide, the potassium ion between the reactant and the product, it looks the exact same. The hydroxide ion is, however, reacting with a magnesium to form the magnesium hydroxide solid. Similarly, the nitrate is just there to bring the magnesium ion. So our potassium ion and our nitrate ion are both spectator ions. Now, a more elegant form of an equation is our net ionic equation. The net ionic equation, we take our ionic equation and we remove spectator ions. This will allow us to focus in on what is actually doing the reaction, the key components of our reaction. So what we would do is we'd take our ionic equation that we have here, and we would cancel out the things that are the same on both sides. So we have 2 potassium on the left, we got 2 potassium ions on the right. These will cancel each other out, and so we would not include them in our net ionic equation. Similarly, our 2 nitrates on the left and 2 nitrates on the right, these remain unchanged, so they are spectator ions, so we will not use them in our net ionic equation. We are left with 2 hydroxide ions reacting with magnesium ions to form our magnesium hydroxide precipitant. So the purpose of the net ionic equation is to focus our attention on the components that are actually participating in the reaction. In the case of the ionic equation, it's to show what we actually have in solution, And the purpose of the molecular equation is to give us an idea of where everything originally came from. So for net ionic equations, we are really only interested in those components that are participating in the reaction. We could look at another reaction, calcium chloride reacting with silver nitrate to form silver chloride and calcium nitrate. You'll notice that our calcium chloride is aqueous, our silver nitrate is aqueous, our silver chloride is listed as being a solid, and our calcium nitrate is listed as being aqueous. We could also look back at our solubility tables. All chlorides are soluble except silver, mercury, and lead. Calcium is not one of those, and so calcium chloride will be soluble. All nitrates are soluble without exception, so the silver nitrate will be soluble. Silver chloride, all chlorides are soluble except silver, mercury, and lead. So this will form a precipitant. And then calcium nitrate, all nitrates are soluble, and so the calcium nitrate will be soluble. What that tells us is that everything that's listed here as being aqueous will actually break apart in solution. So we won't have calcium chloride, we will have calcium ions separated from chloride ions. And we won't have silver nitrate, we will have silver ions and nitrate ions. We will have the calcium chloride as a solid because these two will bind together and form a solid. So we will get the ionic compound silver chloride. The calcium nitrate, because it's soluble, it will break apart into calcium ions and nitrate ions. So the process of writing our net ionic equation is, number one, start out when you're starting this process of learning how to write net ionic equations, start out by writing the molecular equation. Look through each one of your components and determine, is it soluble or not? Based on that, we would write down either our aqueous or our solid. Once you have that, anything that is aqueous, if it is an ionic compound, is going to break apart into its cation and anion. So our silver chloride stays together, the calcium and the nitrate come apart. Okay, now to get from our ionic equation to our net ionic equation, what you will do is look at the reactants and the products. Anything that is the same on the left-hand side and the right-hand side, we will cancel out. So we will get rid of our calcium 2+ because it is the same on both sides. We have it as both a reactant and as a product. Our nitrate ions, they will also cancel out. We have 2 nitrate ions on the left, 2 nitrate ions on the right, and so the nitrate ions are spectator ions. What is left is, well, as written, 2 chloride ions plus 2 silver ions go to 2 silver chloride solids. And because we try to use the lowest common denominator, we would divide everything by 2 to give us our net ionic equation, which is 1 chloride reacts with 1 silver to form 1 silver chloride. We leave out the spectator ions because they do not participate in the reaction, and therefore they are not considered important in considering the reaction that we're looking at. Now, solubility itself is a form of equilibrium. You have an equilibrium between the solid and the ions that it breaks down into. While we do say that some compounds are insoluble, it's not completely true. All ionic compounds will dissolve in water to some degree. However, many of the components have such low solubilities that to all practical purpose, they don't break apart. If only 1 or 2 atoms are to be found in a liter of water, it's fairly sufficient to say that the thing is insoluble, right? So typically insoluble means that your concentrations are sub parts per trillion in water, and so there's realistically not very much of the compound that dissolves. Okay, so all compounds will dissolve to some degree, but when we're talking about insoluble compounds, that degree is exceptionally small. Could be just a couple atoms of, or a couple molecules of our compound break apart to form the ions, but otherwise it all stays in the solid. Now we can apply the concept of equilibrium to salts dissolving and use the equilibrium constant for the process to measure the relative solubilities in water. Now, because the process of having something dissolve is itself a form of equilibrium, it will have an equilibrium constant. In order to denote that this is the equilibrium constant for something dissolving, we use a special K value. It is K subscript SP. The SP means solubility product. So when we're talking about the solubility product, what we are referring to is the equilibrium constant for the dissociation of a solid salt into its aqueous ions. Okay, so that is what we will be calling a solubility product. It just means that it is the equilibrium constant for the solid dissolving. Because it has its own subscript, the reaction is written out in a very particular way. We are focused on the dissolving of the solid. We are focused on the dissolving of the solid into the solution, and so our reactant will be the solid, and the products will be the products of the dissolution process. So the reactants will be our solid, the products will be the aqueous ions in solution. Because this is equilibrium, it follows the exact same rules that we had before. The equilibrium constant is our products raised to their respective powers divided by our reactants, leaving out solids and liquids. So when we're writing down or trying to determine the equilibrium constant expression for a solubility product type problem, we have our products raised to their respective coefficients divided by, well, nothing, right? Not to say that it's 0, but it's divided by essentially 1, right? The concentration of our solid is a constant. Solids and pure liquids, you cannot change their concentration. If you want to half their amount, you half their volume, and so you reduce both the number of moles and the volume in half, and so the concentration stayed the same. Because the concentration of solids and pure liquids is constant, it gets lumped in to our KSP value here. So we do not put it on the right-hand side because it's already being accounted for on the left-hand side. So the KSP is going to work the exact same way that we did with previous equilibrium problems. We will be using ice tables to figure out our concentrations. The values for KSP can vary widely. Something like barium fluoride would be considered soluble. It has a KSP value of 2.45 times 10 to the negative fifth. However, things like sulfides, which are considered insoluble, if we look at copper sulfide, it has an equilibrium constant of 1.27 times 10 to the negative 36th power. What this tells us is if we take a bunch of copper sulfide, put it into a liter of water, we will see a very, very, very low concentration of either copper ions or sulfide ions. In fact, in many cases, this, depending on what you're doing, this will likely be below your detection limit. Similarly, iron sulfide, all sulfides are insoluble. Iron sulfide is no exception. It has a very low equilibrium constant for solubility. So the KSP value is very low. If we look at something that is considered soluble, like calcium fluoride, right? If we look at something that is considered to be soluble, like calcium sulfate, we can see that the equilibrium constant, the KSP, it's still a small number, but it is not nearly as small as the things that are considered insoluble. So the calcium sulfate equilibrium constant is 7.10 times 10 to the negative fifth. This would typically be considered something that is either moderately soluble or soluble. Now, there are a couple terms that we will use when we are referring to or trying to get an idea of the relative solubility of something. So solubility is related to the KSP. The lower the KSP value is, or the smaller the KSP value is, the less soluble something will be. Conversely, the greater the KSP value, the greater the solubility is. We will typically be expressing solubilities either as the molar solubility or the mass solubility. Each one of these is how much of our solid were we able to dissolve per liter of solution. The molar solubility is how many moles of our solute were we able to get to dissolve into 1 liter of our solvent. The mass solubility is the same thing except in grams. So this is what weight of solute were we able to get to dissolve per liter of solution. Both of these types of solubilities represent the maximum amount of solid that we can get to dissolve in a solution. Most of the time it will be the X in the ice table for a solubility reaction, or in the case of the mass solubility, X times the molecular weight for the solute. So now let's look at a problem where we are trying to determine both the molar and mass solubility of lead chloride, or lead 2 chloride, in solution. We're given our KSP of 1.17 times 10 to the negative fifth, which means this is a somewhat soluble solution. Okay, so we got our lead chloride breaks apart into lead 2 plus and 2 chloride ions. So we are going to follow the same procedure that we did before for our previous equilibriums. The first thing we would do is write out our balanced chemical equation, giving ourselves enough space to make it into an ice table. Our equation is already written out, so all we need to do is make this into an ice table. So I for initial, C for change, E for equilibrium. Now, because solids are left out of our equilibrium equation, we don't actually need to know what the concentration is. And so I'm just going to draw a vertical line, meaning that this number here is irrelevant to our calculation. If we read the problem, it doesn't say anything about us having lead or chloride ions in solution to start with. So our values for both of these will be 0. We don't have alternate sources of lead. Perhaps, we could have like a lead nitrate, giving us additional lead ions beyond what we would get from our lead chloride dissolving. Similarly, we could use potassium chloride or sodium chloride to give us some chloride ions beyond what we would get from our lead chloride. However, this particular problem does not say anything about that. So, if we have 0 for our concentration of our products, then these must go up by some value X. So this will go up by X, and because there's a 2 in front of the chloride, this will go up by 2 times X. So at equilibrium, this will be X, and this will be 2X. So if we're writing out our K value, our equilibrium constant expression, KSP, because we're looking at a solubility product, that would be our products over our reactants raised to their respective powers, leaving out solids. So in this case, we would just have our products. So this would be the concentration of lead 2 plus and the concentration of chloride ions raised to the second power. If we plug in our values, we would have X for our lead, and this would be times 2x squared. Now this is a place where a lot of people make mistakes when they're trying to work out these problems. They write out 2x squared without including the set of parentheses around the 2x. The 2 also gets squared. So this would give us x times essentially 4x squared, or 4x to the third power. This right here is 4x squared, not 2x squared. So our KSP, we can now set our 4x to the third equal to our KSP. We want to solve for x, so we will divide both sides by 4. And then, well, that will get rid of our 4 on the left. And then we want x all by itself, so we will take the cubed root of both sides. Another way of doing the cubed root, and one that you can do on your calculator, is raise it to the 1/3 power. Right? So the cubed root of a is equal to a to the 1/3 power. Okay, so taking our values here, this gives us x is equal to the cubed root of our KSP, which is 1.17 times 10 to the negative fifth divided by 4. If you plug this into your calculator, you will get 0.014301 molar. In terms of significant figures, our K value has 3, so our value here will have 3. So essentially our X is equal to 0.0143 molar. This X value is our molar solubility. It is the number of moles of our original salt, the lead chloride, that will dissolve up into solution. So this is the moles of solid that dissolves per liter of solution. So that's our molar solubility. The mass solubility is the same general idea, except we got to convert the moles into grams. So we will take our 0.0143 moles per liter, and this is moles, X is the moles of the lead chloride that dissolved. So this would be PbCl2 that dissolved. And we want to know how many grams dissolve per liter. And so we will have multiply this by our molecular weight, grams on top, moles on bottom. For every 1 mole, the lead chloride weighs 278.1 grams. This will give us 3.9771 grams. Again, we have 3 sig figs from our molar solubility, and so we would have that as our answer. And so our mass solubility would be equal to 3.98 grams per liter, right? So what this is telling us is that if we have a liter of solution, the maximum amount of lead chloride that we could get to dissolve in it would be 3.98 grams into that 1 liter.